Somewhere, right now, in a galaxy so distant that its light will never reach us, a star is dying. And because of a single, quiet fact about the universe we live in, we will never know it happened. Not because we lack the telescopes, not because we lack the patience, but because the space between us and that galaxy is stretching faster than light itself can. Cross it. That sentence should stop you. It stopped me the first time I really understood it, because buried inside it is what I'm Sul's. From light we think of it as the scariest prediction in modern physics. Not an asteroid, not a black hole, not even the death of our sun. Something quieter, something built into the very fabric of space and time. And to understand why it should frighten you, we need to start at the beginning. Not the beginning of the universe, but the beginning of our modern understanding of what space and time actually are. For most of human history, space was just the stage, and time was just the clock. Newton gave us a universe of absolute space, a fixed, unchanging grid, and absolute time, ticking the same everywhere, for everyone, always. It felt obvious. It felt true. It matched everything we could see with the naked eye. And it was wrong. Not wrong in the sense of being useless. Newton's equations still send rockets to the moon, but wrong in the deeper sense that the universe simply does not work the way our intuition insists it must. The person who first saw through the illusion was a young patent clerk in Bern, Switzerland, doing physics in his spare time because no university would hire him. Albert Einstein asked a question so simple a child could pose it, and so radical that it took the greatest minds of his era years to accept the answer. What would you see, he asked, if you could ride alongside a beam of light? Chase a beam of light fast enough, Newtonian physics says, and you should eventually catch up to it. The light should appear to slow down relative to you, the way a car in front of you appears to slow down as you close the distance. But Einstein realized this couldn't be right, because Maxwell's equations, the equations that describe electricity, magnetism, and light itself, insisted that light always travels at exactly the same speed, no matter how fast you yourself are moving. Chase it at 99% the speed of light, and it still races away from you at the same speed as if you were standing still. That's not a small technical detail. That's a wrecking ball swung at everything we thought we understood about space and time. Because if the speed of light is fixed, if it truly never changes, then something else has to stops. And what gives, Einstein realized, is the very thing we thought was unshakable, the flow of time itself. Here is the strange truth that special relativity forces on us. Time is not a universal metronome ticking the same beat for everyone in the cosmos. Time is personal. Time is local. A clock on a speeding spaceship ticks slower from the perspective of someone standing still than a clock on the ground. This isn't an illusion caused by faulty instruments. It is what time actually does. We've confirmed it directly. Atomic clocks flown on airplanes fall out of sync with identical clocks left on the ground by exactly the amount Einstein's equations predict. GPS satellites have to correct for this every single day, or your phone's map would drift off by miles within hours. Time bends. Time stretches. And once you accept that time is not absolute, you're forced to accept something even stranger, that space and time are not two separate things at all. They are stitched together into a single fabric, which physicists call space-time. And that fabric, it turns out, is not rigid. It can curve. It can ripple. It can stretch. That was Einstein's first great insight, special relativity, published in 1905. But he wasn't finished. For the next decade, he wrestled with a harder question. If space and time are one flexible fabric, what role does gravity play? The answer came to him, he later said, as the happiest thought of his life. Imagine a person falling freely off a rooftop, say, in the days before Einstein worried much about safety regulations for thought experiments. While falling, that person feels weightless. They don't feel the pull of gravity at all. From their point of view, they might as well be floating in empty space. This led Einstein to a staggering conclusion. Gravity is not a force reaching out and grabbing objects the way Newton imagined it. Gravity is the shape of space-time itself. Massive objects, stars, planets, black holes, bend and warp the fabric around them, and other objects simply follow the curves in that warped fabric. The Earth doesn't orbit the sun because some invisible rope tugs it inward. The Earth orbits the sun because the sun's sport, and the sun's mass has curved the space-time around it into something like a valley, and the Earth is simply rolling along the easiest path through that valley. Gravity, in other words, is geometry. This picture, general relativity, completed in 1915, has been tested more times, in more ways, with more precision than almost any other idea in the history of science. It predicted that light itself would bend around massive objects, confirmed spectacularly during a solar eclipse in 1919 that made Einstein a global celebrity overnight. It predicted that time runs slower near massive objects, which is why astronauts on the International Space Station, despite moving fast enough to slow their clocks down, actually age very slightly faster than people on Earth because they're farther from our planet's gravitational pull. It predicted black holes, regions where space-time curves so extremely that not even light can escape, decades before anyone had direct evidence they existed, and in 2019 we finally photographed one. It predicted gravitational waves, ripples in space-time itself, caused by cataclysmic events like colliding black holes, and in 2015 we detected them directly, 100 years after Einstein first wrote down the equations that demanded they exist. Space-time is not a backdrop. It is a dynamic, physical thing, capable of stretching, warping, rippling, and this is the piece we need for our scary prediction, expanding. Because here's where the story turns cosmic. If space-time itself can bend and ripple, could it also, on the largest scales, be changing shape across the entire universe? In the late 1920s, an astronomer named Edwin Hubble pointed a telescope at distant galaxies and noticed something extraordinary. Their light was shifted toward the red end of the spectrum, and the more distant the galaxy, the greater the shift. The natural explanation was that these galaxies were rushing away from us, and the farther away they were, the faster they were receding. Einstein's own equations, when applied to the universe as a whole, had already hinted at this possibility, though Einstein himself initially found it so unsettling that he added a fudge factor to his equations just to force the universe to sit still. He later called this his greatest blunder, because the universe isn't sitting still at all. It's expanding, and if you run the expansion backward, rewinding the cosmic film, you reach a moment, roughly 13.8 billion years ago, when everything we can observe, all the galaxies, all the stars, all the matter and energy in the visible universe, was compressed into an unimaginably hot, dense state. We call that moment the Big Bang. Now, I want to clear up a common misconception, because it trips up almost everyone the first time they hear about this. The Big Bang was not an explosion happening at some particular point in space, with matter flying outward into an empty void that was already there. There was no empty void waiting. Space itself came into being and began expanding. Asking where did the Big Bang happen is a bit like asking where is north of the North Pole. The question assumes a kind of spatial framework that simply doesn't apply. Space was not a container that the Big Bang happened inside of. Space was, and is, the very thing that has been expanding ever since. Picture a loaf of raisin bread rising in the oven. Every raisin sees every other raisin moving away from it. Not because the raisins are flying through the dough, but because the dough itself, the space between them, is expanding. That's a rough but genuinely useful picture of our universe. Every galaxy sees every other distant galaxy receding, not because they're rocketing through space, but because space itself is stretching between them. For decades, cosmologists assumed this expansion had to be slowing down. Gravity, after all, pulls things together. Every galaxy tugs on every other galaxy, and that mutual attraction should act like a brake on cosmic expansion. Scientists in the 1990s set out to measure exactly how much the expansion was decelerating using distant exploding stars called supernovae as cosmic mile markers. In 1998, two independent teams announced a result so unexpected that many astronomers initially assumed it must be an error. The expansion of the universe is not slowing down. It is speeding up. Something is pushing galaxies apart faster and faster, overpowering gravity on the largest scales. We don't fully understand what this something is. We've given it a name, dark energy, but a name is not an explanation. What we do know is that it appears to make up roughly 70% of all the energy in the torus, and its effect is to accelerate the expansion of space itself relentlessly forever, as far as our best equations can tell. And this is where our scary prediction starts to take shape. If the expansion of space is accelerating, and if it continues to accelerate indefinitely, then there will come a time, unimaginably far in the future, but a real and calculable time, nonetheless, when every galaxy outside our own small cosmic neighborhood will be receding from us faster than the speed of light. Now, nothing can move through space faster than light. That much of Einstein's original insight still holds. But space itself is not a thing that has to obey that speed limit. Space can stretch as fast as it likes. The distance between two galaxies can grow faster than light without anything actually traveling faster than light, because it's the space between them expanding, not either galaxy moving through space. Once a galaxy crosses that threshold, its light can never reach us again. It doesn't disappear. It doesn't get destroyed. It simply becomes permanently, physically unreachable, cut off from us by the accelerating stretch of the universe itself, forever. Sit with that for a moment, because most people, when they first hear it, assume it's a problem for the far future, and therefore not worth worrying about. But that's exactly what makes it the scariest prediction in modern physics. Not that it will happen suddenly, but that it is already happening quietly, every single day, and there is nothing anyone, anywhere, can ever do to stop it. Right now, galaxies are crossing that horizon, one by one, winking out of any possibility of future contact, not because anything violent happened to them, but simply because the space between us and them stretched a little too far. Extrapolate this forward, and the picture becomes almost unbearably lonely. In roughly 100 billion years, cosmologists estimate, an observer on Earth, or whatever remains of Earth by then, would look up and see essentially nothing beyond our own local group of gravitationally bound galaxies. The rest of the universe won't have been destroyed. It will simply have receded beyond the cosmic horizon, forever unreachable, forever unobservable, as if it had never existed at all. Future civilizations, if any survive that long, may have no way of even knowing the Big Bang happened, no way of detecting the expansion, no way of reconstructing the very story we've just told. The evidence will have literally run away from them, carried off by the same expanding fabric of space that once carried the light of the Big Bang toward us. This single prediction, sometimes called the cosmic horizon problem, or the future isolation of bound galactic structures, connects directly to some of the deepest open questions in physics, including the ones I've spent much of my career on. Because if space and time can behave this strangely on the largest scales, we have to ask, what are space and time actually made of at the smallest scales? This is where string theory enters the picture. Ordinary particle physics treats electrons, quarks, and photons as point-like objects with no internal structure. String theory proposes something different, that if you could zoom in far enough, far beyond what any particle accelerator on Earth could ever achieve, you'd find that these apparent points are actually tiny, vibrating loops or strands of energy, which we call strings. Just as a violin string vibrating in different patterns produces different musical notes, a fundamental string vibrating in different patterns produces what we perceive as different particles. An electron and a photon in this picture aren't fundamentally different kinds of stuff. They're the same kind of string, vibrating in different ways. Why does this matter for our story about the fate of the universe? Because string theory, in its most common formulations, requires far more dimensions of space than the 3 we experience, often 6 or 7 additional spatial dimensions, curled up so tightly that we'd never notice them in ordinary life, like a garden hose that looks like a one-dimensional line from a distance, but reveals a hidden circular dimension when you look up close. These extra dimensions can be shaped in an enormous number of different ways, and different shapes would produce universes with different physical laws, different particle masses, different force strengths, potentially even a different value for that mysterious dark energy that stirs tearing our universe apart. This has led some physicists to a genuinely mind-bending idea that our universe might be just one among a vast landscape of possible universes, each with its own version of the laws of physics, each shaped by its own hidden geometry of curled-up dimensions. If that's true, the accelerating expansion we observe and the eventual isolation it guarantees might just be one outcome among countless others, playing out differently in universes we will never see and can never visit, separated from us, not just by distance, but by the fabric of reality itself. Now, I promised you this story would eventually reach the aliens, and here's where the threads converge in a way that I find genuinely haunting. Enrico Fermi, sitting at a lunch table with colleagues in 1950, posed a deceptively simple question that has haunted physicists and astronomers ever since. Given how many stars exist, how many of them likely host planets, and how much time the universe or the same has had for life to arise and civilizations to develop, where is everybody? If intelligent life is even moderately common, we should expect to see some evidence of it by now. Radio signals, megastructures, probes, something. Instead, as far as our instruments can tell, we see silence. Absolute, total silence. This is the Fermi paradox, and there are dozens of proposed solutions. Maybe intelligent life is exceedingly rare. Maybe civilizations tend to destroy themselves before they can reach the stars. Maybe they're out there but simply too far away or too different from us to detect. But our journey through space, time, the Big Bang, and the accelerating expansion of the universe adds a new and deeply unsettling wrinkle to this old puzzle. Because even if the universe is teeming with intelligent civilizations, even if every single star we can currently observe hosts a thriving alien society, the accelerating expansion of space means that the window for any two civilizations to ever discover each other, communicate, or meet is not infinite. It is closing. It has always been closing. Every year, more galaxies slip permanently beyond our cosmic horizon, taking with them any civilizations they might contain, any signals they might have sent, any chance we ever had of knowing they existed. We are not just isolated by distance. We are isolated by time itself, racing against an expansion that never slows down and never reverses. Perhaps, somewhere out there, right now, another civilization is looking up at their own sky, wondering why it's so quiet, unaware that some of the answer lies not in the rarity of life, but in the relentless, silent stretching of space itself, carrying potential neighbors beyond the reach of any signal, any spacecraft, any hope of contact, forever. And this, I think, is why this prediction deserves the title of the scariest in modern physics. It isn't the kind of scary that keeps you up worrying about an asteroid strike or a rogue black hole, threats you could imagine surviving, evading, or preparing for. It's a scary that operates on a scale so vast, so patient, and so utterly indifferent that no amount of preparation, no advance in technology, no civilization, however brilliant or however long-lived, could ever outrun it. It is written into the geometry of space-time itself, the same geometry Einstein uncovered by imagining a man falling off a roof, the same geometry that gave us black holes and gravitational waves and the birth of the universe in the Big Bang. Dark energy will keep pushing galaxies apart faster and faster for as long as the equations we currently understand continue to hold. And unless something changes in our understanding of physics, unless there's a sorting of Dean mechanism, some feature of string theory's landscape of possible universes, some quantum effect we haven't yet discovered that causes dark energy to weaken or reverse, the far future of our universe is one of overwhelming, permanent, cosmic isolation. But I don't want to leave you only with the fear, because that's not really the spirit in which physicists explore these ideas. There's something genuinely magnificent about being able to calculate the ultimate fate of muncher of the cosmos at all, about a species of curious primates on a small rocky planet using nothing but mathematics and light gathered from ancient stars, figuring out how the universe began, how gravity bends space and time, what matter is made of at its most fundamental level, and how the story of everything might eventually end. That we can even ask these questions, let alone begin to answer them, is itself an extraordinary triumph. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible at all. Every insight we've walked through today, the bending of space-time, the birth of the cosmos in a Big Bang, the vibrating strings that may underlie all matter, the silent expansion that's being spirit and heaven slowly isolating every galaxy from every other, is a testament to that comprehensibility. We may be small, temporary, and destined for cosmic isolation on a timescale almost too vast to imagine. But for now, in this brief cosmic moment, we are here, we are looking up, and we understand more about the fabric of reality than any generation before us ever has. And maybe that, more than anything else, is the real story. Not simply that the universe is expanding away from us, but that for a fleeting instant, in the vastness of space and time, curious minds like ours were here to notice.